Hi everyone. So in this video we introduce a very important concept that's commonly used in deep learning, which is basically the idea of mini batch algorithms. That the algorithm basically processes the training data in batches. So traditionally the word batch is used has been used for to refer to the whole training set, and mini batch is a group of examples. So not the whole training set, but because these algorithms became so widespread that now basically batch refers to many batch. So batch is another keyword that's used to refer to a group of examples. And the idea is very simple. So instead of computing the gradient of the loss with respect to the whole set of training examples and then updating the parameters or choosing the weight parameters based on that gradient. No, we do it iteratively based on groups of examples. So I pick a group of 10 examples. Let's say I have 1,000 examples as my training set. I pick 10 out of these 1,000, and then I compute the gradient of the loss with respect only to these 10 examples, and then I compute the parameter update in the direction of the negative gradient, or basically in the direction of minimizing that cost. And then I pick another set of examples and so on, right? So there are two key ideas behind the motivation of doing this mini batch approach instead of optimizing over the whole training set at once. The first one is basically the standard error, or the square root of the variance of the standard error of the mean estimated from n samples. So if I want to estimate the mean of that true data generating process, and I compute that mean by just averaging over a set of n examples, then the standard error equals sigma over square root n, right? Where sigma is the standard deviation of the true data generating process, which we don't know, and square root n is basically square root the number of examples. So the error shrinks proportional to the square root of the number of examples, right? So that means that the gain diminishes that I get from increasing n, right? So that's why having n very large may not be very beneficial, because an n small can give me an error that's similar, right? So the standard error is typically used to measure how much my estimate would vary based on different groups of examples, right? So this variation in the estimate would decrease you would not gain much by increasing the size significantly, right? So the square root doesn't grow between 100 and 1,000. It doesn't grow by much, right? So that's why that's one reason why minimizing the set of training examples by which over which you compute one parameter update, right, can be very beneficial computationally at a cost in terms of the error of the estimation that's not very significant, right? So that's the first reason. The second reason is basically this iterative procedure of computing parameter updates can be very beneficial, and can be very beneficial for the following reason. My training set could contain redundancies, right? So actually when I include a lot of examples, these examples might not add anything, so this is assuming that the training examples are independent, the square root n thing. But actually, if there are redundancies in this data, then these examples are not adding anything. It's just more computation, right? And moreover, they are not just adding. It's not that they are not adding anything. They might be hurting me, because they might be making me a biased estimate of the gradient, right? But when I take only few examples and these examples are independent, that could give me a higher chance of having an unbiased estimate of the gradient, right? So that, and the other advantage, so one advantage is it increases the likelihood of having an unbiased estimate, a true estimate of the gradient, right? There is no bias resulting from redundancy in the data, right? And the other advantage is that maybe I can compute the gradient with respect to different examples in parallel, right? So I could exploit parallel computational resources, which is commonly existing anyway in the technology of behind graphical processing units, right? I could exploit that for computing the gradient with respect to different examples in parallel, and sometimes even with different many batches in parallel. So doing the computation in parallel can speed up things even more. There is a statistical advantage from minimizing the set, is that I have a higher chance of obtaining an unbiased gradient. The error in the mean doesn't shrink by much as I increase or as the training set size, or as the size of training examples used to compute the gradient increases beyond a certain limit, right? So all these are factors. And the iterative procedure is that instead, so maybe I compute the gradient and it's a biased gradient estimate. I compute the parameter update. It's a bad parameter update. But then in the next time, I will correct that parameter update, right? So the chance of having these training iterations, because the mini batch size is small, that gives me a chance to correct my trajectory, right? And that's why in all of this section, we will discuss all of these algorithms that really draws a trajectory across the parameter space, right? In order to find a good minimum for the cost function. But that trajectory, how you draw that trajectory or how you navigate this trajectory becomes especially important because you are not computing the gradient at once. Because every time you introduce diversity basically in the training procedure. So every time I draw a new set of examples, right? And because this set is drawn at random, right? Through like a random realization from the training set. That's why the word stochastic comes in stochastic gradient descent, or these many batch methods are formally called stochastic many batch methods. The stochasticity comes from the fact that I am drawing the many batch at random, right? So to recap, the standard error doesn't go down by much, so I can afford to have a small mini batch, and I could have a statistical advantage because I could avoid redundancies in the training examples used for computing the gradient, and the iterative procedure used for computing the parameter updates could be advantageous because it adds robustness to the training procedure. And the last thing is computational, is maybe I could afford, depending on the nature of the neural network architecture that we are optimizing, maybe we can afford to compute the gradient and the parameter updates corresponding to different examples in parallel. Thank you.